Hello, in today's lecture, we are going to discuss further Laplace's equation spherical polar coordinates, and more specifically, we are going to discuss the cases of non-azimuthal symmetry. That is the yesterday that we were discussing, and we found that the solutions are quite in some radial part would be there, and some angular part would be given by spherical harmonics, which I had listed yesterday, and so we're going to start from there only. So just give me a minute so that I can share the screen. Okay. Okay. So this is what we were discussing yesterday. And yesterday, as you know, that we were doing this Laplace's equation only, and Laplace's equation in spherical polar coordinates only. And more specifically, we were discussing the non-azimuthal symmetry. That is, we were discussing that if my like equation is dependent upon. Okay, sorry. So we were discussing the cases of non-azimuthal symmetry. That is, just give me a minute. I think the last thing, yeah. So this is what we were discussing. So we were discussing that what would be the complete solution for the Laplace's equation in spherical polar coordinates. And it was the case without the azimuthal symmetry. It was the case without the azimuthal symmetry. And without the azimuthal symmetry. Okay, sorry. Just give me a minute. Okay, so it was the case without the azimuthal symmetry. So without azimuthal, initially when we were talking, we were considering that there's an azimuthal symmetry. That is there is as such no phi dependence, and if there is no phi dependence, then the solution will be in the Legendre's polynomial, will be in the form of Legendre's polynomial, and some radial part would be there. Is that clear? But now, if instead of this when there is an without azimuthal symmetry, there would be some phi dependent part as well. So these parts will come, and when these two are written together, these are called as your spherical harmonics. These two together are called as your spherical harmonics. So this term together is called as your spherical harmonics. Okay. Okay. So both of these terms together are called as spherical harmonics. Here it is. Okay, so these terms are called as your spherical harmonics, and we illustrated like a few of the spherical harmonics I also listed yesterday. And overall, you should also understand that the spherical harmonics are orthogonal to each other by a weight function. Like you have the sine theta here, d theta, d phi, and overall this will be like Kronecker delta LL dash and Kronecker delta MM dash. Okay, and in general, the formulation for finding the spherical harmonics is this. Overall, I told you to remember all these things or probably have an idea of all these things, because time and again you'll find that these will be repeated, and most often you will not find them in examination. So so that is one thing that needs to be understood. Let us do a question and understand how to go about it. So let us consider a sphere of radius r. Consider a sphere of radius capital R having a surface potential, having a surface potential. And what is that surface potential? Surface potential is given by phi as a function of theta and phi, and that is given by surface potential is given by phi naught, and then you have this sine theta, and then you have this sine phi, and we need to obtain potential anywhere inside. So we need to obtain potential anywhere inside. Okay, so the sphere now you can see that there is a there's a phi dependent term as well. Okay, so you just take some, I think this phi would get, you will get confused. So just take as V here. So their potential is given by phi naught sine theta sine phi, and we need to obtain potential anywhere inside. So yesterday itself I told you that the potential here, all right, that the potential V for non-azimuthal symmetry non-azimuthal symmetry is given by VR theta phi, and that would be equals to summation AL r raised to power L ALM r raised to power L plus BLM upon r raised to power L plus 1, and then instead of PL cos theta you have simply यहाँ पे spherical harmonics, that is YLM theta comma phi. Okay, so this is how you get the potential for non-azimuthal symmetry. So when you had this azimuthal symmetry, instead of YLM theta comma phi, you simply had a Legend's polynomial, that is PL cos theta. Now instead of that, uh, as I told you earlier, you will have this term. So you see here it is. Uh, uh, Here it is. Like this entire term is called as YLM theta comma phi. And instead of L, I have written LM, so that you must be aware that it's just not L, there are M's also. Okay. So in general, you have to understand, you can write M here as well. I have not written M, so I'll write M here also and M here also. Okay. So this is how you write your potential. Now you understand, uh, as R tends to infinite, that is for outside cases, for the potential for outside the sphere, you can clearly see that this particular term will go towards infinity. Now, as r tends to infinity, your potential should be 0. It implies your ALM should be 0. Because if ALM survives, then what happens? Then this particular term will blow up. So potential outside in general is given by summation BLM upon r raised to power L plus 1. And then you have the spherical harmonic like theta comma phi. And what is V inside? Now, since if R tends to 0, then this term will blow up. So BLM must be 0, else there will be a source term, or you can see that there will be a Dirac delta term there. Sort of Dirac delta sort of term, that is, it will blow up to infinity. So overall, you have to see that inside this particular term goes to 0, and your potential can be written as ALM, and you can write it as YLM theta comma phi. I hope it is clear. So this is how you're going to write. Now your potential is given as sine theta sine phi and phi naught. Just see, I've told you yesterday, if there is sine theta, then necessarily you can see that this would be some 2, 1. Like you can see, because in 2, 1 you had this sine theta. Whenever you had this even kind of thing, so whenever you had this 0, if m was 0, then it is simply PL thing, like PL cos theta जैसे behave करता है वैसे ही आएगा. So if it is 0, that is, if there is no m term, then it is simply the way your P2 behaves. So it is 3 cos square theta minus 1 upon 2, and you can see. But if there is m term, then instead of cos theta, you may have sine theta. Okay. So one thing is very much clear. Also, you can see that this alone has sine theta term only. So it does not have cos theta, it does not have sine square theta. So most possibly this is one place where we can have where we can stick our thought to. So I'll just write here so that you don't forget it. So y11 is, so I'll write it here. As I know that my y11 is minus root over 3 upon 8 pi, and then I have this sine theta, and then I have this e to the power iota phi. Okay, this is how it is. Okay, so this we have to remember. This is y11. Now, if you just see that your potential on the surface is given by phi naught sine theta sine phi. So on the surface, your r is capital R. So I'll write on the surface of the sphere, on the surface of the sphere, potential, that is at r equals to r, my potential is given by phi naught sine theta and sine phi. So what I will do, I will simply write this potential at r, and that at r equals to r, and there will be some theta and phi functions also. And so this will be like this will be like I'll write it once more. So it will be I will have to see. It will be like phi naught. So minus here, phi naught sine theta and sine phi. Now instead of sine phi, what I will do? I will simply write it as e की power iota phi minus e की power minus iota phi divided by 2 iota. Is that clear? So that somehow I can write my potential on the surface in the terms of some linear combination of my spherical harmonics. And also I told you yesterday that y L minus m is simply minus 1 raised to power m y L m theta comma phi. Is that clear? So this is something that I told you yesterday, that instead of finding instead of finding 1 minus 1, you just use this particular formula, so that if you remember this, then you can remember the entire thing. I hope it is clear till now. Okay, have I made some mistake or somewhere? I don't know. Overall, it is, I think this is fine. Is that clear till now? ये समझ में आ रहा है ऊपर से आ रहा है. So what I'll do, I'll simply multiply it with root over 3 upon 8 pi and multiply it with by root over 8 pi upon 3. Okay, I'll deliberately do so. I'll deliberately multiply it with root over 3 upon 8 pi and then multiply it with root over 8 pi upon 3. Okay, so why I'm doing it, so that I can write, and there is a phi naught also, don't forget about it. So my potential as a function of r equals to r theta and phi, just like that. Okay, and just give me a minute. Okay, where I was, I think it was. Sorry, where I was, कहाँ गया ये? हाँ सर, ये रहा. So it will be like इसको क्या करेंगे? इसको just place it inside. So if I place it inside and this phi naught is outside, so you just write root over 8 pi upon 3. And since I have divided, like I have written sine phi in terms of this, so this 2 pi also comes out. Take 2 pi also outside. You take 2 pi, 2 iota also, sorry, 2 iota also outside. And then you have this phi naught also written here. And then inside you see, inside you have root over 3 upon 8 pi. And then you have the sine theta e की power iota phi. Okay. And then you have this minus, and this is root over 3 upon 8 pi. And then you have this sine theta e की power minus iota. Is that clear? I hope it is clear. कहाँ गई अल्पना? गई गई पता नहीं चलेगी. नहीं गई ना, चलो गुड. चलो, so what is this? This is, I think, if I write it in terms of y11, so is it not y11 with a negative sign? Okay. And if I take, see, I told you y1 minus 1 would be negative of y11. अगर थोड़ा सा ध्यान से देखें, so if I want to write my y1 minus 1, it is simply equals to, sorry, क्या minus 5 भी आता है. Okay, if I have not written minus 5, then it will be a problem. Just give me a minute. इधर भी minus 5 आना चाहिए, else it will be a problem. Okay, okay. So minus 5 आएगा, otherwise गलत हो जाएगा. So overall understand this will be the case. So if I just write this as minus y11, and here if I just write like it is minus 1 1, And what it is? What do you think it is? So is it not minus y1 minus 1? Is that clear? So it is y1 minus 1. So why it is so? So for example, if y11 had a negative here, so instead of negative, now it will have positive. It will have positive, and there will be a negative sign here. So like theta comma minus y. So this is how it is. Like this will be a negative, negative, positive. So overall, there is a negative sign. If I take that negative sign common out, so this will like v as the function of theta and phi, because we are on the surface, is given by phi naught negative. Negative is something that I am not worried about. This is 2 iota. This is root over 8 pi upon 3. I'm here also not worried. And here it is y11 and plus y1 minus. So this is how you can write your potential on the surface. So potential on the surface, you can clearly see there are only terms corresponding to L equals to 1 and M equals to plus minus 1. Okay, so there are only two terms, that is L equals to 1 and M equal to plus minus 1. Are there only in the expression? Are there in the expression? Are there in the expression? Now, if I want to find the potential inside, see, if I want to find the potential inside, one piece of information I've got, that only L equal to 1 and M equal to plus minus 1 terms would be there. All other terms would be 0. If you just compare both of the sides, because here it is like in this fashion. So you can see that your potential on the surface has only two terms, that is y11 and y1 minus 1. And I know that my potential is continuous. So if I just take at r equals to capital R, if I just take at r equal to capital R, and I think there would be some r raised to power L term also here. Okay, if I take r equals to capital R, then this expansion should be equal to this. And overall, I have to understand that only L equals to 1 and M equals to plus minus 1 would survive. So here I would write that potential inside, anywhere inside. So these are like not difficult question, but you have to remember certain things. So potential inside is given by summation ALM, and then you have this R raised to power L, and then you have the spherical harmonic by LM theta comma. And you have to remember that only L equals to 1 and M equals to plus minus 1 term would survive. All other terms are 0. So this will give you potential inside, and potential inside will be simply, if I just write L equals to 1, so there would be A1 minus 1. Here I will write R raised to power 1, and then this is y, and then this is 1 minus 1 plus A11, and then you have R here, and then you have this, I think y, I think this is 1 comma 1. Okay, now if you compare both of the side, both of these things, you can clearly see that if I write, and then there would be R somewhere. I have forgotten R here also. There would be R somewhere. I don't know. अच्छा R है ही नहीं क्या? So you have to divide by R, I think. Okay, so overall understand, this is the potential on the surface. This is the potential on the surface. This is potential anywhere inside, because you can see that potential any on the surface. If I take this, like मैं क्या समझाने की कोशिश कर रहा हूँ समझो. If I want to take limiting case R tends to R, potential inside, and I have to write potential at R, then from here I can clearly see that only y11 and y minus 1 should be there. Because if I expand this in entirety, there would be all those terms like L equal to 0 would be there, M equal to 0 would be there, L equal to 2, M equal to 0, and all those terms, like there would be all those possible combinations. But we have to only select the possible combinations which have this y11 and y1 minus, like 1 and minus. So you just compare both of them and you will be able to find A1 minus 1 and A11. So if you find A11 in A1 minus 1, you can replace it here, and then you can find the potential anywhere inside. Is that clear, or should I repeat it all over again?
भैया repeat करूँगा please.
चलो वापस आओ. So consider a sphere of radius r having surface potential so and so, and we need to obtain potential anywhere inside. Okay, now what I told you, that inside potential will be governed by this term ALM r raised to power L YLM cos theta theta comma phi, and outside it will be governed by BLM r raised to power L plus 1 YLM theta comma phi. Is that clear? Now, if I'm saying that on the surface it is given by phi naught sine theta sine phi, so what I have done, I have eased this expression, or you can say that I have tried to write, I'm trying to write this sine phi in terms of spherical harmonics. Why? Because see, it will be convenient for me. So what I've done, since on the surface it is given phi naught sine theta sine phi, so this will be like V r theta phi. It will be phi naught sine theta, and instead of sine phi, I've written e ki power iota phi minus e ki power minus iota phi divided by 2 iota. Is that clear? Like e ki power iota phi would be sine phi plus iota sine, sorry, cos phi plus iota sine phi minus, and then you can, like, this is quite clear. Okay. So, and I have multiplied it with root over 3 pi 8 pi, again multiplied it by root over 8 pi upon 3. So overall this is 1, but overall uh, this constant root over 8 pi upon 3 I'm taking out, phi naught I'm taking out, 2 pi I'm taking out, and inside you can see that this root over 3 upon 8 pi when multiplied with sine theta e ki power iota phi, and then there would be another term minus root over 3 upon 8 pi, then this is sine theta and this is e ki power minus iota phi. Okay. Now understand that this particular term is your minus y11. See, y11 क्या होता है? Root over 3 upon 8 pi sine theta e की power iota phi. This negative you take common out, and you can absorb this negative in the phi naught itself if you want to. Otherwise, the potential would come as negative. Okay, and this particular potential, you can see this particular, sorry, term, you can see it is y1 minus 1. See, y1 minus 1 क्या होगा? Y1 minus 1 would be minus 1 की power 1 y11 theta minus 5. So instead of y11, I would have एक तो नेगेटिव साइन आएगा, y1 minus 1 आगे तो नेगेटिव नेगेटिव पॉजिटिव, रूट ओवर 3/8 by sin theta e की पावर माइनस आएगा. So this will be your y1 minus. Is that clear? यहाँ तक समझ में आया?
हाँ भैया.
Okay, so मैंने क्या किया? What I have done is I have written this potential on the surface of sphere in terms of linear combinations of spherical harmonics. So my potential on the surface is given by minus phi naught upon 2 iota root over 8 pi upon 3, and then this is y11 plus y1 minus. Is that clear? Now, see what I'm trying to say, that I have to find potential inside, and potential is continuous. Since potential is continuous function on the boundary also, so V inside ki limit should be equals to potential at, like, V inside ki limit r tends to capital R should be equals to potential on the surface of the sphere. So if I write potential inside, तो potential inside की अगर मैं limit ले लूँ, मान लेते हैं, let's say if I want to take the limit r tends to capital R, so only two terms should survive, no? बिकॉज अगर इसको एक्सपैंड करोगे आर इक्वल टू कैपिटल आर रख के, यहां से दोनों कंपेयर करो, तो ओनली यही तो टर्म आना चाहिए. इज दैट क्लियर और नॉट क्लियर? देखो मेरी बात समझो, इतना सिंपल है. ये रहा आपका सरफेस. ओके, यहाँ आपका पोटेंशियल दे रखा है कुछ लीनियर कॉम्बिनेशन ऑफ y11 प्लस y1 माइनस 1. फॉरगेट अबाउट कॉन्स्टेंट्स. ओके, एंड इनसाइड आपका पोटेंशियल है ALM r रेज टू पावर L YLM. Okay, and theta comma phi, you know, and these are all summation. Is particular point पे, like on the surface, your potential is continuous. It implies what? If I place ALM r raised to power L YLM, this particular potential is inside potential, and if I take the limit r tends to R, that is if I place r equal to capital R, then this particular potential should be some linear combination of y11 and y1 minus 1, isn't it? So only L equals to 1 and M equals to plus minus 1 would survive. This is what I'm trying to say. Is that clear or is that not clear now? Is
हाँ
that
भैया.
clear? है ना जी? Okay. So overall, you just find this A11 and A1 minus 1. So A11, sorry, at R equals to R, if I place potential inside in general is given by this. Now on the surface, if I write, this will be like A1 minus 1 R raised to power like 1 only because L is 1. And then you have this y1 minus 1 plus a11 r y1 1, it will be equals to what? It will be equals to minus of इस माइनस को हटा ही देते हैं, तो ऊपर नीचे आयोटा से मल्टीप्लाई कर दो, सो ऊपर नीचे आयोटा से मल्टीप्लाई किया तो कितना है, फाइव नॉट iota upon 2, and this is root over 8 pi upon 3, and this is y1 1 plus y1 minus 1, and just try to find what will be a1 minus 1. So your a1 minus 1 would be iota phi naught upon 2 root over 8 pi upon 3 and divided by 1 upon r, and similarly your a1 minus 1 would also be iota phi naught upon 2 root over 8 pi upon 3 1 upon. Is that clear? Now, after having found a11 and sorry, this would be like a11. After having found a11 and a1 minus 1, you can clearly find potential inside. So potential inside is given by summation ALM r raised to power L YLM theta comma phi, and all you need to do is you have to expand this particular thing only for L equals to 1 and M equals to plus minus. This is what I'm trying to say. So if you expand this thing, then you will find that this is equals to, if you place 1 1 1 1 is iota phi naught upon 2 is 2 को भूल जाते हैं, so it is like root over 2 pi upon 3, because 8 root 8 is 2 root 2. So I've written r here, and then you have this a11. It implies what? Here you will have this r, and you will just place r here, r upon r, and then you have this term like y11, okay? And then again you have, don't forget that term, okay? And then you have again iota phi naught upon, like this has been dissolved. Both of these constant terms are same, so I'm just writing it here. And then you have this y1 1 plus y1 minus 1. Is that clear or is that not clear? So this is how you can write your potential, and if you want to solve it, you can solve that as well. I have no issues. Is that clear or is that not clear? कहाँ चले गए सारे सारे? Is that clear or is that not clear?
Okay.
Okay. वो कहाँ चला गया दूसरा बंदा? ठीक है, so this is how you can write, and y11 and y1 minus 1, you know that चाहो तो तुम इसको भी expand कर सकते हो और चाहो तो. So y11 would be what? y11 would be, ये दो दो मैंने क्यों लिखे? हाँ तो बोल दिया, बड़ी आसानी से गलती बोल रहे हो. Like this is okay. This will not come back. इसलिए हाँ नहीं बोलना है जब तक नई चीज समझ में आए तब तक. ठीक है, सो दिस इज व्हाट इट इज. सोचो ना, अभी मैंने क्या किया? व्हाट आई हैव डन, आई हैव सिंपली रिप्लेस्ड y11 एंड y1 माइनस मैंने तो रिप्लेस किया है मैंने, सॉरी, l इक्वल्स टू 1 एंड m इक्वल्स टू प्लस माइनस 1 वाले एक्सप्रेशन ही तो करेंगे. सो उन दोनों के कांस्टेंट तो सेम ही आने वाले. कांस्टेंट्स आर गोइंग टू कम द सेम. देखो ये दोनों कांस्टेंट सेम ही तो है, और आर की जगह क्या आएगा? स्मॉल आर, और एक नीचे की तरफ कैपिटल आर, एंड दिस इज y1 माइनस 1. एंड इफ यू वांट टू अगेन और भी ज्यादा ढंग से सॉल्व करना है, देन देखो 1 y11 एंड प्लस y1 माइनस 1, ये क्या होता है जल्दी पता करो. y11 कितना होता है? रूट ओवर कितना होता है? सम 3/8 पाई ऐसी कुछ होता है. रूट ओवर 3/8 पाई, देन यू हैव दिस साइन थीटा, एंड यू हैव e की पावर आयोटा फाई, एंड y माइनस 1 कितना होगा? माइनस, सॉरी यहाँ पे एक माइनस आएगा, यहाँ पे प्लस आएगा. रूट ओवर 3/8 पाई, एंड देन यू हैव दिस साइन थीटा, एंड देन यू हैव e की पावर माइनस आयोटा. इज दैट क्लियर? दिस इज हाउ इट इज. मैंने लिख के बताया ना बेटा, y11 यही होता है, और y1 माइनस
आप
1 करोगे तो फाइव की जगह नेगेटिव आएगा, एंड देन दिस नेगेटिव विल गेट डिसॉल्व. थोड़े लंबे क्वेश्चन है, इसलिए जनरली एग्जाम में नहीं पूछ, जनरली क्या आज तक कोई भी नहीं पूछ रहा है इनमें से कुछ भी. So if you want, I will do a few more questions, but overall this is certainly not going to be asked in examination because this is too long an exercise for you. So overall this will be like minus 2 iota, and then there would be sine phi. ओके, बिकॉज ई की पावर आयोटा फाइव के आगे एक नेगेटिव लग रहा है, ई की पावर माइनस आयोटा फाइव माइनस ई की पावर e की power minus iota 5 minus e की power iota 5 will be minus 2 iota sin 5. So if you replace this here, so what we'll get? So your phi inside anywhere inside will be given by iota phi naught root over 2 pi upon 3, and then you have this r upon capital R, and then you have this minus 2 iota sine theta sine phi, and then you have this root over 3 upon 8 pi. This is how it is. So if you cancel it out, so root over 3 will get cancelled, 5 will get cancelled, 2 is 2 and 8 is 4, 4 and this will get cancelled. Is that clear? So overall, all these things would get cancelled, and phi inside, phi near, potential anywhere inside is written as iota, iota is minus 1, minus minus plus. So you have this phi naught r upon capital R sine theta sine phi. So this is how your potential would behave anywhere inside. It will be function of r, theta, and phi. So this is the most general result when you do not have any azimuthal symmetry. Is that clear or not? Is that clear or not clear?
हाँ
अभी तो
भैया.
ठीक है. So this is how you're going to do it. It is very easy in the sense थोड़ा सा calculation ज़्यादा है, and possibly you have to remember all these things. Like अगर if you're not able to remember, then it is a closure for you in the exam. Okay. Because I hope examiner does not ask these constants, but overall, even if you know that these are some case, if you just write some case, you can at least understand the form of the solution. If you even don't remember all these things, root over 3 by 8 pi, at least form of the solution you can understand. That is very much clear. So I hope in examination they don't go very they don't expect you to remember these constants. So overall, if the form is being asked, then I think this can be done in examination also. All you need to have certain sense of understanding. वो बार बार पढ़ने से आएगी. The more you just write them down in front of you, every time you just see them, you just try to remember them. So basically यहाँ पे 1 है तो यहाँ 1 ही आएगा, यहाँ 2 है तो e की पावर 2 ही आएगा, यहाँ 0 है तो there will be no. So there is only one way that I remember all these things, that if m is 0, then both of them will be like Legendre's polynomial only. Like constant को भूल जाओ, this is 3 cos square theta minus 1 upon 2. And if m is there, then instead of cos theta, you will have sin theta. In all of these expressions, you can see sin theta. And if y11, remember this sin theta, y22, remember there is sin square theta, and in mixed terms, there is sin theta cos theta. This is how I remember, this is what I'm telling you. Okay, now yesterday also we did that if potential is given, then this is how you do. Now instead, if some surface charge density is glued over the surface, on the surface of a sphere. Now instead, if a surface charge density is glued over the surface. So what should I write? Is glued over the surface. Over the surface. Let us take some example and try to understand from that example itself. So let us say that if the surface charge density initially we had, now we'll take sigma naught only sine 2 theta, and then I'll take sine phi. So if a surface charge density is glued over the surface of the sphere, then how to find potential inside and outside? Then how to find potential inside as well outside? This is what we have to see. So as I've told you yesterday also, that if you're given potential, if you're given surface charge density, then you have to use the condition that the electric field, the normal component of electric field, is discontinuous on the surface. If electric field is discontinuous on the surface, that implies what? Del V upon del R at R equals to R plus. So this will be like minus. So I'll write outside plus del V upon del R inside at R equals to capital R and R equals to R. So basically what is it means, this will be equals to what? Sigma upon epsilon. Yesterday we told now, इलेक्ट्रिक फील्ड का नॉर्मल कंपोनेंट आउटसाइड माइनस इलेक्ट्रिक फील्ड का कंपोनेंट इन परपेंडिकुलर कंपोनेंट इनसाइड विल गिव यू सिग्मा अपॉन एप्सिलॉन नॉट. And what is electric field का normal component? This is minus del V upon the normal component n. And what is normal component for on the surface? On the surface, the normal component is the radial direction. So I'll simply use this and minus del V upon del R plus, and this will be R minus. I hope it is clear. Okay, and this will be equals to what? This will be equal to sigma naught sine 2 theta and sine phi. Now, what is the best strategy? Best strategy is to write all these things in terms of spherical harmonics so that life become easy for us. What I'll do, I'll simply write this. So first, let us write sigma naught sine theta, and this is, I think, no, sine 2 theta, sorry, sine 2 theta, and this is sine phi. I will try to write it in terms of spherical harmonics. तो कम से कम हमें ये तो पता चले कि what all terms are surviving. And here you will have e की power iota phi minus e की power minus iota phi divided by 2 iota. Is that clear? And there is some 2 also, right? Okay, so overall I can write it as sine naught, like sigma naught sine theta, and then there will be cos theta, and this 2 gets cancelled, and there is some iota also, so I'll keep iota here, and there will be some, okay, and there will be some e की power iota phi minus e की power minus iota phi. This is what is that clear? like, अब तो सोचो मैंने क्या बताया था कि देखो y11 में क्या आएगा, अगर m का टर्म है then y11 will be some function of sine theta, y22 will be some sine square theta, will have some sine square theta, obviously some e की power 2 iota phi would be there, some e की power iota phi would be there. So what, by only guesswork I can say, by only guessing, but whatever association I made, I can say that this will be y11 or y2 y11 नहीं सॉरी y21 and y2. Are you getting my point? मतलब तुम्हें ये समझ में आ रहा है कि मैं कर क्या रहा हूँ, what I'm trying to explain, or are you not getting it?
नहीं भैया, गेटिंग
I'm I'm trying to, मतलब होता है ना वो टिप्स एंड ट्रिक्स वाली बात कर रहा हूँ मैं, कि किस तरीके से तुम्हें याद रहेगा ये चीज समझने की कोशिश करो. अगर m की जगह 0 है, you do not have any sine term, you will simply have some cos terms, और वो pl cos theta की तरह बिहेव करेगा. तो this is how you're going to remember these two things. y00 constant भूल जाओ उसको, y11 के अंदर you will have sin theta, y22 में you are going to have sin square theta. बाकी ये कांस्टेंट टर्म याद रहे तो ठीक, ना याद रहे तो भी चलेगा, बट ओवरऑल दिस फॉर्म यू शुड रिमेंबर. अब देखो यहाँ पर ध्यान से, y22 में sin स्क्वायर थीटा, लेकिन y21 में क्या आ रहा है, देयर इज अ sin थीटा cosine थीटा टर्म. सो ये यहाँ से समझ में आना चाहिए. आर यू गेटिंग माय पॉइंट? सो आई विल राइट इट हियर सो दैट तुम्हारा कैलकुलेशन इजी रह जाए, बिकॉज and make a list of these spherical harmonics somewhere, because this is like again going to get repeated in hydrogen atom. So in any way you have to remember this. y21 would be minus root over 15 upon 8 pi, and I think there is sine theta, and then there will be some cos theta, and then there will be e की power iota phi. Okay, so I think if I just multiply it like y2 1, so what I will do, I will multiply it with the 15 upon 8 pi, and again multiply it with 8 pi upon 15 root over. Okay, so I will simply write it as root over 8 pi upon 15 sigma naught upon iota, and then there will be this term, so you just multiply it inside. So root over 15 upon 8 pi, if I multiply inside, so what I will get, this will be y minus of y2 1. Okay, and then this will be, I think, again a negative, because see y y2 minus 1 क्या होगा, y2 minus 1 will be again minus 1 raised to power m here is 1, and it is y2 1, and this is theta minus phi. So overall this is how it is. So minus 1 की power 1 is minus y21 would be again same to same, this will be like y21 only, but with this like minus theta. So I will write minus of y2. ये चीज समझ में आई कि नहीं आई, कि ऊपर से चली गई? जो दूसरा टर्म दिख रहा है बेटा, है ना, दिस इज माइनस आयोटा फाइव, एक नेगेटिव आगे लगा ही हुआ है. आई थिंक कुछ गलती कर रहे हैं क्यों? अच्छा, एक गलती होगी शायद, एक बार लिख ही लेते हैं ना. सो दिस इज लाइक y y2 कुछ गलती करेंगे, y2 -1 कितना को ढंग से लिख लेते हैं, y2 -1 would be I think -1 into y21. So y21 कितना है, y21 is minus minus plus, so this is root over 15/8 by सही था, ठीक है, sin theta cos theta, and then this will be like e की power minus iota 5. So overall this will be positive. So overall ये सारा जो equation है, this will be y2 minus and negative both side. And you take iota, multiply iota below and above, so you'll get iota square below, so that this negative sign gets absorbed. So this is iota sigma naught root over 8 pi upon 15, and this is y21 plus y2 minus 1. So you are now able to understand that your surface charge density in terms of your spherical harmonics, I can write it in this way. This is my first step. Okay. Now, another thing is I have to understand that there will be two boundary conditions. The first boundary condition is that my potential must be continuous. The first one, acha, what will be potential inside? Potential inside, I'll write it here so that you don't get confused. This is, I think, r raised to power L, and summation is implied, and this is y Lm theta comma phi. This is potential inside. And what is potential outside? Potential outside is given by summation BLM r raised to power L y Lm theta comma phi. So what we'll use, we'll use two conditions. The first, the continuity of potential at the boundary. Continuity of potential at the boundary, which will give you what? Which will give you that ALM r raised to power L should be equals to, sorry, divided by L. Sorry, and this will be like BLM r ki power L plus 1. So in general, BLM is equals to what? It is equals to ALM r ki power 2L plus 1. I hope it is clear. Or is that not clear? Okay, this is something that you should know. Or is that not clear to you? ये चीज समझ पाए? Now we are going to use the another condition that your electric field normal component is discontinuous on the surface, and that we are going to see in the next lecture. Okay, so let us meet in the next lecture.